We're live from NASA's flying observatory called SOFIA. We have instrument operator Chris Trin and mission director Charlie Kaminsky, and they're going to take us on a tour of SOFIA. Let's go up, guys. So we're boarding the observatory now. We've entered SOFIA. This is the main mission control center for the observatory where we conduct our science observations from 40,000 feet. And here's mission director Charlie Kaminsky to tell us more about what we're seeing.
Hello there. As you saw, it was raining outside today. And so one of the reasons we have this observatory is so that we can get above all this rain and get above all the atmospheric water vapor. So let's come over and we'll take a look at where I work. They're still trying to set it up. It's been off for a few days, so we're having a little issue with getting the computer started, but this is where the mission director sits here. This is where I live for 10-hour flights. I sit and watch the entire observatory from here and make sure and coordinate everything that's going on. And next to me is where the flight planner sits. We have also a mission director, but it's like pilot, co-pilot we have here. Also a mission director who coordinates and makes sure that we're on the flight path that we want to be on. It's a very interesting flight path that we fly with SOFIA. We have to set up a long time in advance how we do this to look at the stars we want to look at. So you can see each leg is a different star or different target we're looking at. And we are a telescope just like any telescope on Earth, except that we're flying up very high, and most telescopes on the ground you can rotate the telescope and tilt it up and down to look at the different stars. And we can tilt it up and down, as you'll see a little bit, but to rotate we have to move the whole airplane. So that's why we fly these different paths, to look at the different stars we want to look at in the sky. So let's see, what can I tell you? It is an observatory. We're flying at 43,000 feet, so we do have safety equipment just like on any airplane. We have well, actually underneath we have an oxygen bottle that I can walk around with. We do have some safety equipment behind every chair, just like you have on your airlines, and we do have water vests and whatnot also.
Can you walk us through the flight path?
Sure. So I guess come around. Well, this is an old one just from last month. We took off from Palmdale, California, and we flew straight east, pretty much through Las Vegas, and then we got on our first star, which is a setup star, and we get everything coordinated and get everything lined up, our gyros and everything lined up, and then we start on our science leg. We turn on this way. So as we're flying up, looking at our science target, whatever galaxy or star forming or star dying, we're flying up and the telescope looks to the left. So you just have to think we're looking at some star in the west when we're flying up north, and then we fly down this way, we're looking to the northeast with the telescope, etc. So you fly down, come here. Each one of these legs is like an hour. Well, the whole flight is 10 hours. This is Iowa here. Tells you we fly about 5,000 miles when we fly. And we keep track of what the airplane's doing. It's important to know the altitude and speed and things. The pilots fly the airplane, but it's nice to know what they're doing in case we have to, my job is to try to keep us on the line if the winds move us off of that, because the air traffic control doesn't like it when we wander too far. So that's a big part of my job.
And Charlie, how did you get a job doing this? What's your background?
My background is I ran a telescope in Hawaii on Mauna Kea for 20 years called the Infrared Telescope Facility, IRTF, on top of Mauna Kea. And I also am a pilot. I a flight instructor for small airplanes, not for big ones. And so it's just natural to mix astronomy. I've studied astronomy in school. And
Thank you. We're going to move to the telescope now.
okay. Get this cord going.
Can you tell us what we're seeing right now?
This is the back end of our telescope, and right now there's no instrument, there's no science instrument installed, but that big black tarp that's on there now is where the telescope, where we mount our instrument. They're really big instruments to look in the infrared. And so the light from the telescope, you know, it's raining out there, so we can't open it up and show you the telescope itself, but there's a big bulkhead. You see that white thing surrounding everything. That bulkhead is protecting us. We're inside here in the short sleeve environment, just like any 747 or any big airplane you fly on. We don't have to wear oxygen masks. We don't have to worry about anything. We're in a regular atmosphere just like you're flying on an airplane. But behind that bulkhead is open, that's air. I mean, it's just open, thin air from the stratosphere. There's no window in front of our telescope. It's just a big 10-foot hole in the side of the airplane that the telescope looks out through. So we have to protect ourselves from the pressure by this pressure bulkhead. But we have a way of the light coming through that and getting to the instrument. The next instrument that we'll be installing is called Fifi, and I think I'll turn it over to Chris to talk about that if he wants to talk. Here's my microphone.
Thanks, Chris. Can you give us some facts about the telescope and then go into more about the instrument?
Sure, good morning. So you wanted some facts about the telescope. In terms of astronomy, our porting stability is good to like half an arc second, which basically means, if you guys do any target shooting, an inch at 100 yards is about 1 arc minute. So if you divide that by 60, you actually get, and divide that by a half, and you actually get our pointing stability over, the course of, minutes.
And how big is the telescope?
Telescope is 2.5 meters, which is the same size as the Hubble Space Telescope.
Great, and can you show us where we control the telescope during the flight?
Sure. So the telescope operators sit to the left of the mission director as you're facing the back of the aircraft over in this station here. So from these control panels, the telescope operators essentially use them to get on to the field that we're looking at, and they use the track stars in the field to actually maintain our pointing stability, and we're actually able to take instruments with the science instrument without any image distortion due to the efforts of the telescope operator.
And how do we keep the telescope still during flight?
That's an excellent question. That's actually probably the biggest engineering challenge that we face. If you've ever, tried to take a picture from a moving car, try rolling down the windows and, just keeping your arms stable. That's difficult enough, right? So here we are in an aircraft flying at 45,000 feet, trying to keep a 17 metric ton telescope stable throughout the entire flight. So there's several engineering designs that enable that to happen. The first thing is that Charlie mentioned that we have this 10-foot open door cavity that exposes the telescope to the environment, and so it can experience a lot of shear from wind turbulence. And if you ever look at the outside of SOFIA, unfortunately it's raining outside today, so it's hard for us to show you the outside of the aircraft. You'll see that the fuselage is actually slightly bulged, like you can see in this image here. So just to orient you, this is the back of the aircraft. Here's the tail fin right here. The area around the cavity door is actually slightly bulged, what they call the forward fuselage ramp. And the effect of that is that it actually directs the airflow up and over the telescope cavity, so that from an airflow perspective, the pilots basically see the same thing whether the door is open or closed. And so they've actually commented that they don't even notice when the door is open from a flight perspective, which is pretty amazing when you think about it.
tell us why we put the telescope in the airplanes at all?
Ah, yes. Another excellent question. So, we're an infrared telescope, and a lot of the infrared light that we want to observe and record in our images, it's actually absorbed by the water vapor in the atmosphere. So, the name of the game for us is to actually fly high enough above most of the water vapor. As soon as you get into the stratosphere, at the stratospheric layer of the atmosphere, the water vapor content plummets dramatically. And so being in an aircraft enables us to get to that area where there's very little water vapor and we can actually make the observations that we need and capture the infrared light that we're interested in. You wouldn't be able to do this from a lot of mountaintop observatories. Space telescopes can do it, but they're also quite expensive and it's hard to service your instruments once they get up there.
And can you tell people, do we fly at night?
We do fly at night. There's several reasons for doing so. From being an infrared telescope, it actually, most of our instruments can observe during the day just like they do at night, because the atmosphere is actually not scattering a lot of infrared light. But for as a safety precaution, you don't want to accidentally catch the sun into our telescope, which would, really kind of screw a lot of things up in terms of instrumentation. And so as a safety precaution, we do fly at night.
And what is that dark area in the center? Can you tell us what goes there and why we can't remove the telescope right now?
Sure. So the dark area at the center is essentially where the telescope, which is on the other side of that pressure bulkhead, focuses the light into a small image, and we mount our science instruments at that black hole where we put a detector right at that focus to actually capture the images that scientists need to use in order to do their science. And so, this is kind of a cartoon of what I'm describing there. So this is what you're kind of familiar with here on the right as your normal telescope. The light comes in, it reflects off these mirrors, and then it comes to a focus here, right where this is that black hole. And then this is a cartoon of the science instruments that we mount there. An analogy that you can think of here is, if you do any sort of like high-end digital photography, like you have, lenses of all different sizes and shapes, and you can usually remove them from the camera body with the detector. And so in this analogy, we only have one big lens, but we have a lot of different detectors and camera bodies that we can attach on to the lens.
And we have some folks asking about the German and NASA partnership. Maybe Charlie could tell us more about that.
Yeah, sure. Over to you, Charlie.
It's back to me. So what was the question?
About the partnership between NASA and DLR.
Yeah, okay. So we'll take a wander over to where the telescope operators work. We have that display up now, so we have something to look at. So what we have is NASA has gotten in a partnership with the Germans. The Germans built the 17-ton telescope we have in the back of the airplane. So all that blue stuff is all by German engineering, designed and built by the Germans as their partnership for the SOFIA project. They have many German scientists that want to do this kind of work in the infrared. So 80% of it is NASA money and 20% of it is DLR money, which is their version of NASA back in Germany. So 20% is for the Germans. So they get 20% of the science time, and Americans get 80%. Well, American projects get 80% of the time. This is where the telescope operators sit. Because of the complexity of everything going on with this airplane, we have two telescope operators actually. We have the primary one sits on the right here usually, and then the one on the left is supporting. So we have many displays. These are not all of them up, but one thing I want to point out is we have three different displays. Nothing happening now, but this is a wide field of view. It's about 6 degrees across, so it's pretty much how you would look in the sky. And then this little box here is this whole field, this is a wide field imager, this is a fine field imager, and these are separate telescopes. These are not part of the big telescope. There's actually little telescopes mounted to the big telescope. And then this is looking through the big telescope itself, SOFIA itself. So that little box there is this field of view. So if you find a star here, you put it here, and then if it's up here, you put it here, and then you can see it here.
Great. And can you reiterate where we are and what SOFIA does for the folks who just joined us?
We're in New Zealand right now, Christchurch. Oh, the control.
What does SOFIA stand for?
SOFIA stands for the Stratospheric Observatory for Infrared Astronomy. And this is the control deck. This is where we do all the mission work. This is not where we fly the airplane. The pilots are upstairs. This is a huge 747. So, yeah, scientists sit here, telescope operators sit here, mission directors are behind, watching everything going on. And we have displays all over the place to help everybody see what's going on. And we usually have 25 people or so on board to work the operation.
Putting on all of these stations, right?
Yeah, so mission director sits here. Yeah. Just kind of get a feel for what's going on. You're going to take a trip?
Yeah, I think some folks want to see some images that SOFIA
Oh,
has
some
taken
science.
with the telescope.
Back to Chris.
Back to me. All right, so I actually come to SOFIA from an astronomy research background. So let me take this opportunity to tell you something about the science images over here. The way that I describe it to people, SOFIA is really good at studying really old things or really young things. Really young things tend to form in cocoons of dust, which visible light, which telescopes like the Hubble Space Telescope are sensitive to, can't really view. It can't penetrate through that dust. Whereas with infrared light, because it's longer wavelength, it's easier to escape from these dust cocoons, and when you're looking at infrared light, you can penetrate deeper into them. And so we're really good at studying young things, star formation, or really old things, which throughout their lifetime they're producing and synthesizing a lot of dust, and they eventually explode as something like a supernova and spew out all this dust. And so we've, for hundreds of years have been studying stars, galaxies in the visible wavelength regime, which our eyes are sensitive to. And so SOFIA gives us the opportunity to kind of fill in the gaps of knowledge that we are lacking by studying these systems in the infrared. And so, we've kind of turned SOFIA into a little bit of a museum here. With these images that we've taken and highlighting the different science areas that researchers have been using SOFIA to study. The first one I guess I want to highlight is the galactic center here. Now the center of our galaxy is an area that's renowned for how much dust there is. Like when you try to look at the center of the Milky Way, the reason why you see that dark band is because there's so much dust. And so when you train an infrared telescope on it and take a look at the galactic center, you see a totally different picture because all of a sudden now you can actually probe deeper into it. And so what you're seeing here is the circumnuclear ring around the galactic center. And so, all the dust that would normally be there doesn't show up in this image because we're looking at it in the infrared. And so this is kind of almost the thermal signature of the center of the galaxy, not just the reflected or scattered light that you would normally see in the visible. And so, that's one example of the advantage of using SOFIA is that with, infrared light, you're able to see deeper into dust enshrouded areas. So moving along here, with astrochemistry here, another thing that SOFIA is really good at is that when you start getting more complex molecules, complex organic molecules, these things start to actually radiate a lot of low energy radiation from the vibrations and the rotations of these molecules. And so they just happen to be at the infrared wavelengths that SOFIA is sensitive to. And so when you look at star forming regions, a lot of times SOFIA, when you look at regions like the Orion Nebula, you can actually pick up a lot of these molecular vibration lines that make our studies of star formation easier to do. Okay. The last one that I'm gonna highlight, because it's actually one of my personal favorites, is this one here on comets. Okay, so when I was going through schools, I didn't think that comets were actually all that special. Okay, but what you got to realize is that comets typically come from the outer portions of the solar system, and when you catch comets coming in on their first pass, you're essentially getting a pristine representation of what the solar system was like when it formed. Okay, and so when we capture these comets on their first pass in, we're essentially seeing what the solar system was like when it was formed. And so I remember seeing the first comet, observing my first comet on SOFIA, and really getting an appreciation for that. All right, I'm giving up the mic.
All right, we're going to head up to SOFIA's cockpit now. We're on NASA's Stratospheric Observatory for Infrared Astronomy. We're live from the flight deck, and you can see in the back of the aircraft is the telescope. And if you move to the forward, it's where our telescope operators sit. And this is where our mission directors operate from. And now we're going to go up and see where the pilots sit and keep us steady on our flight. And our next flight is next week. Some people asked where the bathroom was. It's on the other side of this galley. We can actually make coffee in flight. We have refrigerators. We fly 10-hour missions, so it's important to be able to have coffee to keep us awake overnight and warm up our lunch. Thanks, Charlie. And the bathroom's on the other side. So yes, refrigerators, and we're gonna head upstairs. SOFIA is a Boeing 747 SP, which means we have 2 levels on this aircraft. Oh, and this is what's left of SOFIA's days as a commercial aircraft. A few first-class seats where people can sit for takeoff and landing. So we're heading upstairs.
More first class.
A few more seats. Charlie, can I give you the mic?
Sorry. Hi. I got the microphone again, oh boy.
Here we are in the flight deck.
All right, this is my dream job, would be to sit here and actually fly it, but that is not to be, so I sit in the back and drive the telescope. Well, actually, I watch people drive the telescope. So I'm sitting in the pilot seat right now, and it always has 3 crew on this. It's an older airplane, built in 1977, and it was originally built for Pan Am, flying across the Pacific. It was the first, the short plane, the 747 SPs for special performance, was a plane that was able to fly completely across the Pacific Ocean without refueling. It went from Pan Am to United, and then finally to us for SOFIA. In a couple years ago, we upgraded all of the instruments. They used to be the old, what we call steam gauges, or round dials, which you can see in this is where the flight engineer sits. Like I said, there's three crew here, and so the flight engineer's panel looks pretty much like the old way the pilots also looked, but now we have all the glass displays. We have many computer panels now, so it's been modernized. But they have many different ways of navigating, and well, it's a 747. It's very complicated.
And can you discuss for us why it's important for the pilots to coordinate with you downstairs?
All right, so most airplanes you fly from point A to point B, and that's all you do. So all you have to do is fly a flight route, and the air traffic control knows what you want to do, and they say, okay, you're going from here to here, and you have a flight plan that says I'm getting from here to here. We, on the other hand, you saw that picture downstairs, fly all over the place, and different up, down, left, right, and they're always going, where are you going now? We get kind of comments like that. Even though we have a flight plan, it's complicated to most air traffic control people. They're starting to learn about us, but and in fact, once in a while they will ask us, say, are you the airplane that has a big telescope in it? It's kind of fun to talk with them about it. What are you looking at tonight? But the difference is that we don't care the ground track. We don't care from point A to point B what we're doing. All we care about is flying through the air and pointing in the right direction. So if the wind blows us, we don't stay on the same route, same course. We actually drift off. And as we're looking at stars, I actually have to help the pilots try to stay on course. and talk to them and say 1 degree to the left, 1 degree to the right. And so I'm talking to the pilots constantly. So that's one of the things I have to do, is to watch the flight plan downstairs, and also watching the telescope to make sure the telescope can move 3 degrees plus or minus up and down, left and right, as long as we're centered. It can move up and down because we have turbulence. I mean, it's not smooth. It's not on the ground. But the telescope is well engineered, very, very good telescope, gyro stabilized, and but the airplane can move around plus or minus 3 degrees. And so anyway, I coordinate with the pilots if there's turbulence or whatnot, make sure everybody's buckled in. So that's a safety thing as well. That's what I do downstairs. Occasionally we come up here. We are allowed to come up here and talk with the pilots. They're happy to entertain us and talk about things. It's a 10-hour flight, so it's really long, and it's at night.
Can you explain where we are right now?
We are in the cockpit. Is that
outside?
outside? Well, if you see through the window, it's kind of rainy day, but through the window is Christchurch, New Zealand. It's on the South Island of New Zealand. Christchurch, big airport, and that's the control tower for the airport. And there's the ramps and whatnot. So that's where the commercial people all come in, the planes come in and leave. And we're parked in what's called the deep freeze area, this is actually, we're allowed to use this ramp area, which is built for the Antarctic program. And since the Antarctic program is different months, we can come here and use this space. So we actually use the buildings and the ramp area for our airplane during the winter here. It's confusing to people back home, back in America, that down here it's winter time. We just had a winter solstice, so the beginning of winter just started, where you're just enjoying summer right now. It's the beginning of summer. So anyway,
we're gonna go back downstairs.
All right, we're back downstairs, and I'm getting out of the seat.
All right, so now we're gonna go back down. You can see our seating on the second deck of SOFIA, and we're going to walk down the stairs to the main deck one more time. And Chris, can you just wrap it up for us? Tell us what SOFIA stands for and why we're here in New Zealand and on an airplane.
Right, so SOFIA stands for the Stratospheric Observatory for Infrared Astronomy. Like I mentioned earlier, when you think about it, it's more or less self-explanatory, right? We're an infrared telescope. We're in an airplane. We're trying to reach the stratosphere. The water vapor, yes. We're down here in Christchurch, New Zealand, taking advantage of the long nights and the dry air to actually observe the infrared radiation that we want to collect, which normally gets absorbed by the water vapor in the atmosphere. So if we were back at home right now, there'd be quite a lot of moisture in the atmosphere and a lot of different weather systems that really prevent us from executing the flight plan that we originally planned. And so scientifically, it's just very valuable for us to be down here for this time. Not to mention the fact that you see different things in the northern hemisphere and different things in the southern hemisphere. And so being down here, we can observe things like the Large Magellanic Cloud, Small Magellanic Cloud, and other really interesting objects in the southern sky.
So thank you, Chris. Thank you, Charlie, our mission director and our instrument operator from NASA's Flying Observatory, SOFIA, where we fly above 99% of the water vapor in Earth's atmosphere to observe the universe at infrared wavelengths. And goodbye from the main deck of SOFIA.